Hey guys, your boy Chili here. Welcome back to Multithreading C++. In the last video, we encountered our friend, the race condition, and we have bested him in combat, but at what cost? Well, without any kind of synchronization. Of course, we got the wrong answer, but it only took 0.11 seconds. Whereas if we use a mutex, we can ensure that we have the correct answer every time, but it's 6 times slower, which is actually slower than if we just didn't use multithreading at all. So that might lead you to believe that, well, maybe multithreading isn't all it's cracked up to be. But, you know, this is one situation, and there are many. The problem with this situation is that this mutex is getting hammered, 5 million times 4 times. So 20 million times. And it's just too much hammering of the mutex. It can't handle that level of hammering. It's gonna slow you down. But one thing that you should always keep in mind when you're trying to optimize things, when you're trying to speed up a program by multithreading, is, well, I mean, there might require some synchronization here, but can we reduce the amount of synchronization necessary, or can we transfer it to somewhere else? And so yeah, there's two. In the last video, there were 2 elephants in the room that I refused to address, but we're going to address them here. And number one is that this is just, if you just kind of change the way you think about the problem here, you can get a much, much better result. So what's the problem? What can we change here about how we think about the problem? Well, instead of in every single step accumulating into this shared piece of memory, what if we did this? For every worker thread, we gave it its own accumulation variable. And so each thread accumulates into its own separate accumulator. And then when all the threads are done, at the very end, we gather the final results by adding all these accumulators together, which is, it's like if you've got 4 threads, that's 3 additions, right? That's nothing to get the final result. Now, if we do this, each thread has its own place in memory where it's accumulating this stuff. So the threads no longer share memory while they're operating. And so we don't need a mutex at all. We just accumulate into 4 separate places in memory. And then once all the threads have completed, we join here. And this is kind of like our proxy for synchronization. We join the threads, we wait until all of them are completed, and then we take these 4 memory locations, we add them together, we get the final result. And then we don't need a mutex. Mutex doesn't get hammered. All the 4 threads, they can basically run independently. And we just gotta wait for them all to finish and then do a quick little operation that's basically takes 0 time at all. So how does that look? Well, we don't need a mutex, obviously. This thing doesn't need to take in a mutex. Okay, that's fine enough. Now for our sum here, we're gonna do it like this. And if I do this, I believe it will 0 initialize all the elements. I think that's how it works. Although, you know what? Because we don't actually have listed, we haven't specified the size. We'll just do it like this. This is very safe. So we're going to have 1, 2, 3, 4 of these bad boys here. Now, obviously we can't pass this in because it doesn't exist. And for each of these threads, we're going to need to give it its own sum variable to work on. So if I had range v3, I'd probably do an enumerate on this, but whatever. Int I is equal size ti is equal to 0, as long as I is less than 4, I plus plus, and then in here, sum at I. All right, so that seems like it should work, except Now we don't have R, right? Because we don't have our range-based for loop. So we'll just do data sets at I. And that's fine. All right. So this part of it is done. Yeah, and it should be accumulating. And then the result is going to be sim, dim sum, 0 plus, all the stuff. And there's our result. And we don't need this. And that's fine. This thing will just accumulate into, each thread will have its own sum to accumulate into. And everyone should be happy. We should get the same result we had before, which I believe was 1540. Yeah, 1540. And it took 0.29 seconds. All right. So that's obviously an improvement. We've doubled our speed. We've also, we have now officially gotten some benefit out of multithreading, since, without multithreading, how long would it have taken? 0.4 seconds, I believe, is what we got around. Yeah, 0.4, 0.44, whatever. So we're faster than a single-threaded version of this operation, but we're not 4 times faster. We're not even close to 4 times faster. And that's strange, right? Because when you think about it, each one of these threads that we're launching here has its own sum that it is writing to. There's no synchronization happening here, at least none that we're aware of. And yet it's slower. And if you look back, remember I said there were 2 elephants in the room. One of the elephants was obviously that we don't need to have a mutex. We can just sum up to, each thread has its own sum, and then we gather the results at the end. That was elephant number 1. But elephant number 2, you might not have caught. And that was that even without the mutex, the beginning of the video, when I demonstrated the summing into a single variable, even though we weren't doing any synchronization, the time that it took was about the same as we're seeing now. Let me run it again. It took, about 2.25 seconds to do that operation, which is 2.5 times slower than we had before, when we were just accumulating into the first element of this array. So what is that difference? What's happening here? And so this is very interesting. This gets into specifics of architectures of different CPUs. But this is a fairly common architectural quirk that you'll see everywhere. And the basic, the gist of it is when you load, let's say you load this int into your, into your CPU. This int is, 4 bytes. The actual hardware, the circuitry, doesn't just transfer 4 bytes. It transfers a lot more. Most computers are going to have it's not a D. They're going to have DDR RAM, be like DDR4 or whatever. And this DDR RAM, the width of the interface between the RAM and the CPU, it's not 4 bytes. It's a lot more. I don't remember how much. I think it's probably 64 bytes. That's the width of the pipe between the RAM and the CPU. So in a single transfer, it can transfer 64 bytes. And that's what it does. So when you request 4 bytes, what it actually does is it transfers 64 bytes and stores all that in cache. And I mean, the rationale there is, look at this block of 64 bytes. If you request this piece of memory here, the chances of you probably in the future requesting some of this memory is also high. So when we fetch this, we're actually going to fetch in all of this because we have this, 64 byte wide interface here. The speed of transferring 4 bytes and 64 bytes is exactly the same. So we're going to fetch all those 64. And whenever we fetch from memory into the CPU, we store that into cache, because the chances, if you've accessed a memory location once, the chances of you accessing it again in the near future are very high. So we cache that, and we also cache the neighboring 64 bytes. And so what that means is that when you access this variable, you're actually accessing lots of variables in memory. Now here's the thing. Here's where it gets even more complicated. So we've got, you know, I said CPU, but let's call this a core. We've got multiple cores all accessing the memory. Now, the CPU is constructed in such a way that when one core writes to a memory address, that should be immediately visible to all the other cores. If this core writes a 0, this core reads, let's say this piece of memory originally held a 10. This core writes a 0. This core, if it reads, it should get the 0. It should not get the stale 10 value. And you might say, well, that's obvious. If you wrote a 0 into here and this core read from here, it should read the 0. But you have to remember, there's cache. So normally when if a core has this memory location cached, and let's say the cache value was the old value of 10. So this is 10 here, 10 here. If the core says, I want to read this memory location, it's going to read it from the cache because it's like, I don't know how much, it's like 100 times faster. Who knows? It's a hell of a lot faster to read from the cache. So it's not going to fetch from memory if it has it in cache. But if this core writes a 0, then this memory location should contain a 0. But if this core reads and it reads from the cache, it'll get the 10. So what happens is when you have multiple cores accessing the same memory, if one core writes to that, that change has to propagate to all the other cores. And in order for that to happen, there's basically a kind of lock that is happening at the hardware side when multiple cores are, you know, writing and reading from the same memory location. So this is a lock. This is synchronization that you don't write in your code. You're not really aware of it. It's happening seamlessly behind the scenes in order to preserve the coherency of the cache. So that if this core writes a 0, this core is going to read a 0. It's not going to read the stale 10. So there is locking and there is synchronization happening behind the scenes. And it could not, like, I mean, and you might say, okay, yeah, that makes sense. If one thread writes to a single variable, another thread reads, I could see that. But you actually have to be aware of the width of, you know, how much memory the CPU is going to pull in every time it reads. And that depends on the CPU. But I mean, for most modern CPUs, I believe it's 64 bytes. I don't know. Let's look it up. For what the hell? Let's look it up, okay? So here's a page. Zen 3 microarchitecture. L3 cache, L2 cache, L. 64 byte line size. So yeah. And it's been this way for a very long time. So what that means is that if you have, you know, 1, 2, 3, 4 integers beside each other, they're all in the same cache line. So even if you have 4 threads reading and writing to 4 different integers, you're going to have synchronization because they're all reading and writing to the same cache line, which is essentially the same place in memory. And the CPU is going to synchronize that so that each thread sees when one thread writes a value to this cache line, each other of these cores will be able to see that change basically immediately. Will not get a stale value. So how can we test this theory out that this is the problem we're having? Well, let's create a struct. And we'll call this one, I don't know. We'll call this one value. I don't know. And we'll do int v, and we'll do char padding. So if v is 64 bytes, the padding should be 60 bytes. So now if we have a struct like this, what does this mean? Well, this means that each of our v's are going to be in a different cache line because of the padding in between. So now, if this is our v, this is our padding, and then this is our next v, which is in a different cache line. So now, if our threads are all writing to these different v's, they should not suffer from that synchronization. So what are we going to do here? Well, sum I dot v. So now we're going to pass in a reference to each of our v's, to each of our worker threads here. And down here, we're going to add up all the v's. 1, 2, 3. All right, that's beautiful. So what do we expect to happen here? Well, first of all, I expect it to compile, but you never know. It does compile. Okay. So I expect the answer to be correct. Same result. We're doing the same operations. But because the 4... Wait, why are you angry? Reading invalid data from sum. The readable size is 64 bytes, but 128 bytes might be read. Okay, we'll try this. We'll give the v's a default. And how do you like that now? Okay, maybe this warning doesn't mean what I think it means, but yeah, valid index range 0 to 0. That doesn't make any sense. Okay, well, whatever. You know what? We're going to say that IntelliSense is high on its own farts here, and we're going to see what happens when we run this. Okay, we get the correct answer, and look at this. Processing took 1.3 seconds, which is pretty much in line with what we saw when we had no synchronization at all, 1.1. There you go. So now we're actually getting no synchronization because, again, why? Because of our boy here. The padding means that now this stuff is going to be on different cache lines. And so, yeah, the CPU is not going to do that synchronization behind the scenes. There'll be other ways of making sure that this happens. Probably a good one would be just to put the sum in the thread itself and then have the thread basically return the result, but you need more machinery for that. We'll do that. That's what we'll do in the future sometime. But anyways, yeah, it's just something interesting to be aware of, this phenomenon of the cache lines and the synchronization that the CPU does behind the scenes to make sure that there is coherency between all the different caches of the cores. Something to be aware of. But I mean, the main takeaway is, instead of having 4 threads accessing and hammering a single variable in memory and putting a mutex on it, it's better just to have the threads work as much as possible separately, and then at the end, gather those results. And this is probably the simplest example of taking a problem and transforming it a little bit in a way that requires a lot less inter-process synchronization, and that'll give you much better, much more efficient multi-threading. Unfortunately, there are many problems where, you won't be able to do that. It's not going to be that simple, and you're going to need synchronization. And that's the kind of thing that we'll look into in the future. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button. Helps a lot. And I will see you soon with some more C++ multi-threading.